All right, well, here we are again for trig. We're going to be talking about section 3.4, which is the sum to product identities, and actually the vice versa is product to sum as well. Here's what I'm going to do. I'm going to go into the notes, and I want to read you something because it's important for the purposes of this class. So here are the notes. Some of the applications require conversion from sum to products and vice versa. So here are the relevant identities to achieve this. But I make a note. This section right here is part of the reason why these exams are open notes. I really do not hate you, okay? I promise. Look at all these formulas, okay? I have a hard enough time memorizing all of these, and so I wouldn't expect you to do that as well. That's part of the reason I just knew that when we were, starting up this course, there's going to be a lot of just trig identities and so many different conversions, essentially, so many different types of identities that it's practically impossible to keep them all perfectly straight. So we're not going to do that. Instead, I've listed them all here as a reference to you. You can go back, follow along, and see what they look like. And what we're going to do is I'm going to go through a bunch of examples today just to show you what they specifically look like in terms of questions. So let me jump to the whiteboard. Sorry, I've got this glare again right in the middle of my board. It's late at night, and unfortunately I didn't record this during daylight, so we'll just try to work around it as best as we can. So here we're in section 3.4. I'm just going to go through a few questions here, and then we'll see how this goes. So question number 2. This question, so in these questions, it's asking us to write each expression as a sum or difference of two functions. So question 2 is giving us 2 sine of 4x, sine of 2x. Okay, and when you have something like this, really you're just using the conversion. So sine of 4x, sine of 2x. If I flip back to my notes, I'm going to be using this guy right here. Okay, so this is my function we're using for this example. So we've got alpha is 4x, beta is going to be 2x. And the coefficient in front, you can just keep that there, and then we multiply times 1/2, and it was cosine 4x minus 2x. Again, it's just substituting in the formula 4x plus 2x. Okay, so this right here is the same thing as cosine of 2x minus cosine of 4x plus 2x is going to be 6x. Okay, so that is our final answer. Of course, I'm literally right on the mark. Sorry about that. There it is for you. I'm going to try to avoid that as much as I possibly can, but perks of recording late at night, right? It's just, this is what you get. So that's what we have, cosine 2x minus cosine 6x. All right, so now let's go ahead and do question number 4. It's a similar idea. We have cosine of 3x, cosine of 5x. So we can represent this, again, we're using cosine. So if I go back to the notes, this time we'll do cosine would be this guy right here. So we'll be using this section of our notes. So cosine cosine alpha plus beta, cosine alpha minus beta. Let's just go ahead and jump back to our whiteboard and write that out. Is it going to switch? There it is. Okay. So this is going to be 1/2 times, what is it? Cosine 3x plus 5x. And we're going to be adding cosine 3x minus 5x. Sorry, I ran out of space there. So this is equal to 1/2 cosine of 8x plus cosine of negative 2x. Now, here's the thing that's important to remember. You may remember that there's actually a conversion between, if you've got cosine of a negative angle, that's the same as just the positive side. So actually, this can be converted here into just cosine of 2x. So, sorry, there's a bracket there. 1/2 bracket cosine 8x plus cosine of 2x. I guess I don't need the bracket there. So there you have it. So again, that's a specific identity that's from way back when. I can't remember how far back. It's a ways. I think it was maybe in chapter 1. It's a long ways back. So that's what you can do. You can just convert it right there. So that's question 4. Let's go through question 10. A lot of this is just referencing what we already have. So question 10, they're giving us the sine of 105 degrees and the cosine of 15 degrees. And they're actually asking us to find the exact value of what this is. So let me flip back here. Sine cosine is going to be using this, so we'll have 1/2 sine alpha plus beta plus sine alpha minus beta. So let's go ahead and toss this in here. Go back to my board. So this is the same thing as, and I'll save the space here, 1/2 times the sine of 105 degrees plus 15 degrees plus the sine of 105 minus 15 degrees. Okay, and let me jump over this glare here. So this is going to be the same as 1/2 the sine of 105 plus 15 is going to be 120. And I'm adding the sine of, in this case, this is going to work out to being 90, actually. So that's kind of nice. Okay, so here's the thing. You can actually pull these values straight from the unit circle. I told you, everything comes back to the unit circle. If I've been wrong so far this semester, it is like one of the most useful tools out there. So actually, when you work all these out, you can find the values of each of these individual components and what you'll find. So remember, if you track along the unit circle, you'll get an xy value, and the y value is your sine. Okay, so you can actually find the values. So sine of 120 is just going to be whatever you get. In this case, I've already gotten it. It's going to be the square root of 3 over 2, and then sine of 90 is going to be 1. So this is the same thing as the square root of 3 plus 2 all over 4 when you multiply it all out. So that's our final answer. All right, let's go ahead and move on to the next question. Next question is question 20. And here they're asking us to, again, this is another identity question. So write each expression as the product of two functions. So previously we were doing the product to the sum, and now we're doing sum to product. So that's going to be, if you flip to the notes, we're actually going to be looking down at the second section here. So you got sine x, sine y, and it's just a combination of all of these. So here is essentially what we have. I feel like I copied one of these wrong. Hang on just a second. Let me double check my notes. I want to make sure. No, that's all correct. And then that one is, yeah, that's all there. Yeah, okay, so let's go ahead and, oh, actually, there is one that's wrong. This should be a -2 sign. I'll fix that in the notes that I upload, so don't worry. This is a -2 sign, x plus y. Okay. That, drop that minus sign. Oh, boy. All right, so fortunately, that's not the one that we need for this question. The one that we need for this question here is going to be the sine minus sine. So sine of 7 theta minus sine of 3 theta. This is going to be, again, go back to reference. So it's actually going to be this one right here. So 2 cosine x plus y times sine x minus y. So what we got is 2 cosine 7 theta plus 3 theta all over 2 and sine 7 theta minus 3 theta all over 2. Okay, so this works out to being the same thing as 2 cosine 7 plus 3 is 10 theta over 2 is going to be 5 theta. And this is going to be sine of 7 minus 3 is 4 over 2 is going to be 2 theta. Okay, and I haven't been putting my boxes, but you can go ahead and do that as well. All right, let's do question number 32. Same idea. Again, we're going to be using the sum. In this case, I think 32 is asking us to do cosine theta. So this is cosine theta plus cosine theta over 2 is equal to 2 cosine theta plus theta over 2 all over 2 cosine of theta minus theta over 2 all over 2. Okay. So pretty much at this point now it's just a matter of doing some algebra, working things out, getting rid of those complex fractions, and what you'll find is if you work this all out, you'll get 2 times the cosine of 3/4 theta times cosine of 1/4 theta. Or theta over 4, 3 theta over 4, that's fine. You can do it that way as well. So again, it's just a lot of algebra at this point, but I'm confident that you guys can all do that. Okay, let's go ahead and jump to question number 34. Question 34. So these are asking us to do a couple different things. In particular, we just need to verify the identity. So the identity they give us is going to be 2, so 34. 2 sine alpha sine beta is equal to, let me pull the board down a little bit so you can see in case I get to the edge, cosine alpha minus beta times, what's this one? Or sorry, minus cosine of alpha plus beta. Okay. So let's do the right-hand side. We're going to start from the right-hand side and work our way down instead of the left. This way, we've already done a lot of these in the previous section, so that's why I just kind of want to go with it. So we've got cosine of alpha minus beta minus cosine of alpha plus beta. And again, this is using some of the identities that we've already done. So this is the same. I'm going to try to avoid my little section here. This is going to be the same as, so let's do the first one first. So this will be cosine alpha cosine beta minus, or sorry, this is plus sine alpha sine beta And so that's the first part. The second part is going to be minus cosine alpha cosine beta, and I'm running out of space, so I'm going to jump to the next line, plus sine alpha sine beta. Okay? So take a look at what we have. This term right here and this term right here, they're just going to cancel each other out. So I'm literally left with this plus that, which is just exactly what our identity was, 2 sine of alpha sine beta. So that's the nice thing about doing these identities. You don't have to work the left side to the right side. You can pick whichever side you want, but once you work it out, if you get to something that works out nicely, then you're gold. You're solid. So that's how you do that one. Let's do, let me see here. Let's go ahead and do question 40. Question 40. Question 40 is the cosine of 5x minus the cosine of 3x equal to negative 8 sine, this is a weird one, sine squared x times 2 cosine cubed x minus cosine x. Oh boy, this is a kind of a weird one. All right, let's do the difference to product, because those are pretty good to find. So let's see here. And of course, the one that you need is the one that is actually the one I screwed up. So let me, again, I'm going to fix that in the notes, so by the time you open this up, it should be correct. So we've got 2 cosine 5x minus cosine 3x. Let's go ahead and work that out. This is going to be the same, cosine 5x minus cosine 3x is the same thing as, again, just using the definition of the identity, sine 5x plus 3x all over 2 sine of 5x minus 3x all over 2. Okay. So now this is the same thing as just above the glare. So let me try to avoid that again. This is the same thing as, well, let's just simplify it. Minus 2 sine 5x plus 3x is going to be 8x over 2, which is 4x. And then we've got sine of 5 minus 3 is 2x over 2, which is just sine x. Okay, now we can actually use the sine of 4x function and simplify that even further. So that's like the double angle identity from the last section. I don't know if you remember that, but what you can find is that if you go ahead and punch this in, you'll get here, let me see if I can pull it up here. Give me a second. Let me see here. Sine 4x is the same thing as, yep. Sine alpha cosine alpha. So let me pull this up for you. So here's what I'm basically looking at. Okay. This is what I'm looking at right here. And I'm telling you right now, we're going to have to use that in a combination of this as well. So really what we got going on is this is going to convert to a minus. So we've got this minus 2 times another 2. So this is going to be minus 2 times 2 sine of 2x cosine 2x sine of x. Here, sorry, I flipped to the wrong. There we go. Cosine 2x, sine of x. Okay. So now we can actually go even further with these and use the double angle formula again. So you're kind of using multiple iterations of the same formula, which is kind of unique. So this is going to be minus, so the 2 times the minus 2, I'm just going to do this, minus 4. And now the sine 2x is going to be 2 sine x cosine x. The cosine 2x, if we go back to, again, last section, here's another a whole variety of different formulas. Now, you want to use the one that's going to get you what you want. So, we'll flip back, there we go. So if we take a look specifically up here at our solution, one of the things that, okay, it looks like we got the -8. It looks like we've got a sine x. That sine x is going to multiply it out, so that's good. The thing is, we need a cosine squared x minus 1, it looks like. So this is going to be the cosine 2x. Again, let me flip back to my PDF here. The cosine 2x means I'm going to need this one. Okay? So this kind of feels all over the place. We're doing multiple iterations of the double angle formula. So the 2 sine x, cosine x, the cosine 2x, now that's the one that I'm doing, and this is going to be the same as 2 cosine squared x minus 1 times sine x. Okay. It's kind of insane. So this is now my -8. I've got sine x times sine x, which is sine squared x. My cosine, if I distribute that across the board, I'm going to get times 2 cosine cubed x minus cosine x. And that's what we wanted. So that actually, this guy, you can see it matches up exactly with what we got up top. So we're done. So this is kind of a harder one. It's a bit unique and uses some old formulas and identities that we needed. So again, just because we do something doesn't mean we're ever done with it. Hence the unit circle, which continually comes up. So again, things come up pretty regularly, and it's good to have those notes handy in front of you when you're working on these, just so you can see all the different identities at play. So that was question 40. I'm going to do 2 more, and then we're going to call it. So question 48. This one is, again, another identity question. So this one's asking us, it's again just verifying the identity. So we've got sine x plus y times sine x minus y is equal to the sine squared x minus sine squared y. Okay, so this is kind of what we need to do. We need to start here and go there. Again, remember, you can pick either side to work with. In this case, I'm just going to work with the left-hand side because we have the product formulas. So let me go back here and switch to this guy. Okay, so sine xy, x plus y times sine x minus y. X plus y, you can think of that as like alpha. And x minus y is beta. And so you can use this formula right here. So that's what we're going to do. So now what we got is 1/2 times the cosine of x plus y minus x plus y here. So the minus sign is actually distributing to both those. So a minus x and a minus y, which makes it a positive. Okay. And the second part is going to be plus cosine of x plus y minus, or sorry, this is a plus x minus y. Okay, that's a fun one. So this is the same thing as, well, let's just simplify all this. So this is going to be cosine of x plus y minus x plus y. This is going to be 2y. And this is going to be cosine of 2x. And look what we got. We have the double angle formula again. I'm telling you, they keep showing up. It's kind of amazing how it works. All right, so I want sine squared x and sine squared y. So the cosine, remember, if I go back to the section 3.3 notes, I'm going to use this one right here. Okay, we'll use that one. So let's go back to our whiteboard. And again, I'm right on the spot, so let me just jump down beneath it. It's hard. I can see it on the screen, but I can't actually see it here where I'm writing. So it's like, oh yeah, there's a glare there. I can't even tell because it's just the way that the camera's reflecting the light from the ceiling. It's not reflecting it into my eyeball. All right, so this is going to be 1/2 times 1 minus sine squared y minus 1 plus sine squared x. Okay? And sure enough, look what happens. The 1's cancel. I'm left with sine squared x minus... Oh, sorry, this is 2. This is a 2 right there. There's a 2 in front of these. So I'm left with 1/2 times 2 sine squared x minus 2 sine squared y. And the 2's are going to cancel with the 1/2, so this is literally the same as sine squared x minus sine squared y. Okay? And that's our answer. When things all come together, it's pretty amazing. It's pretty beautiful, actually, how it all works. This is part of the reason why I really like Identities a lot, just because it's a mind exercise to use what you know, and it's just building itself. It's just building itself up. So you start with a lot of the basic identities, and then you just keep adding more and more and more to it, and you get to a point where it just takes a little bit of creativity to solve some of these identities, which is really kind of cool. So let's go ahead and do question 50 now. So 50, there's another formula that they list in the notes that I want to show you. And if you go to the very bottom, so if you get functions that look like this, so you get like a coefficient times sine and another coefficient times cosine, you can actually represent it as something completely different, which in this case is just some k constant times sine x plus an alpha. And alpha is an angle. And so, in fact, they actually define what these particular pieces are. So sine of alpha is going to equal this. Cosine of alpha is equal to that. K is just going to be some, it's using the Pythagorean theorem to go ahead and work that all out. So my camera just turned off, so let me turn that back on, and then we'll go through this example so hopefully you can see how it all works out. All right, so here's my camera. Question 50, they are telling us that we need to write the given equation in the form y is equal to k sine x plus alpha, where a measure of alpha is in degrees. And so for question 50, what they're giving us is that y is equal to the square root of 3 sine of x minus cosine of x. Okay, so what we can do is we can actually represent just some of the pieces right off the get-go. I am going to, so let's go ahead and start. So we've got a, this is the formula, a sine x minus, or plus I should say, plus b cosine x is equal to k times some sine of, I guess I don't need that bracket, I just kind of added it in there, k times sine of x plus alpha. So again, you can take the combination of a sine and cosine and turn it into a multiplier times some sine function that it looks like has a transformation applied to it. So what we'll do is we'll represent these functions as our a's, b's, and c's, and then we'll see what happens. So a is equal to the square root of 3, b is equal to a negative 1, and again, based upon the notes here, you can actually get your k value. Let me pull this up. So our k is going to be our a squared plus b squared. Okay, so k is going to be the square root of square root of 3 squared plus negative 1 squared. So this is the same thing. It's equal to the square root of 3 3 plus 1, which is equal to the square root of 4, which is equal to 2. Okay, so there is our k value. And so now what we need to do is we need to look specifically at the points. A and B can actually be thought of as a point. So the point, again, because we've got a sine component and a cosine component, the cosine component represents the x value. I think I flipped this. The point, yeah, so the point can be represented in a unique way. So let me see here. Yeah, so let's go ahead and just take a look at this. We'll just do the cosine and the sine component and see what we get. Okay, so sine of alpha, I'm going to do this way. I don't like the way that I initially did it. I'm just actually going to kind of shoot from the hip here, so bear with me. B is actually going to be, so this is negative 1 all over the square root of a squared plus b squared, which is 2, so this is going to be negative 1/2. The cosine of alpha is equal to, what is it? Cosine of alpha is a, so a is going to equal root 3 over 2. So actually, check this out. The point that we have is going to be root 3 over 2, negative 1 over 2. Okay? Again, if we go off of the unit circle, remember these are cosine values. So cosine alpha, sine alpha. X values and y values, they all work out to be cosine, sine when you look at the unit circle. And actually, let me see if I can go find that. I want to see how this works out. All the way back to section 1. How about that, Mapples? Alright, so I think I just did a whole bunch of talking without actually showing. So let me actually show you really quick what I wrote. So I got my sine of alpha, and I'm again substituting it into the formula that I just had for sine and cosine. You get minus 1/2 and root 3. So the root 3 over 2, that's actually, again, your x value, and your y value is going to be minus 1/2. So this is technically a quadrant 4 angle. Okay? You've got a positive component for the x and negative component for the y, so it has to be in quadrant 4, which means if I go back to the unit circle, I'm looking essentially for square root of 3 minus 1/2. Well, here it is. Check that out. So it shows up down here at 330 degrees, which actually is going to be a minus 30 degree angle. Okay, so actually alpha is equal to minus 30 degrees. Alpha is equal to a minus 30 degrees. So what does that mean? When we plug it into the formula, we know k is equal to 2. Then we go back to our sine of x plus alpha. So in this case, alpha is a minus 30 degrees. So this is a negative 30 degrees right there. Okay. So that's the solution. That's how you get to converting essentially something that looked like this up here into that guy right there. Those are the exact same things. So that's pretty much it. If you wanted to, you could draw a picture and do a right triangle. You can do that as well. But the reality is if you use the unit circle and you know that your x component is just going to be the cosine, the y component's the sine, you can pretty much use that to find all of the different values, and then your angle measure. So that's really it, and I hope you all have a great night, and I will hopefully see you at some point. Well, next semester, I guess, because this whole thing is probably going to keep us out for quite a long time. So anyway, have a good one, and enjoy your evening.